We just finished figuring out how to express the performance of systems operating in a cycle. In other words, how to quantify the performance of systems operating in a cycle. But we didn't say anything about what was going on in the cycle. Were the processes reversible? Were the processes irreversible? Or there will be multiple processes. Is it a mix of reversible and irreversible processes? In this video, what I want to do is address cycles that are fully reversible. All the processes are fully internally reversible. So let's get started and see where we go with that. And so this video is associated with fully reversible cycle performance. So we're going to come up with a way now to quantify a special type of cycle that's fully reversible. Okay, let's recap a little bit just to be sure we're all on the same page. What's a reversible process and what's a cycle? So let's see, reversible process. It's it's a process that can be reversed without leaving any trace on the surroundings. Okay, that's a pretty simple thing to know. And we covered all the different types of things that make processes irreversible. And so we could eliminate those. A cycle is made up of two or more processes that start and end at the same state. Okay, and so the tried and true schematics, it's my hope that you've got this in your head. And you say, well, I don't even need to see those schematics. I have them in my head. That's great. So here's a schematic for our power cycle where we're producing net power or for one single cycle work. Okay, over here for refrigeration or heat pump cycle, wow, W dot net is a negative number, so we're having to invest some power or work in order to transfer heat from cold to hot. A little harder to understand, but I think you got it. Now, what I'm going to do is, rather than droning on and on in a video, I know what the outcome would not be good for that, would it? But I do want to recommend that you at least browse these sections in your book. If you have time, please read these sections 5.6, 5.7, and 5.8. And so it has to do with second law aspects. So that must have something to do with what's reversible and what's irreversible aspects of power cycles and second law associated with that. Okay. 5.7, same idea with refrigeration and heat pump cycles. And 5.8 has to do with Kelvin and Rankine temperature scales, or in other words, absolute temperature discussion. The author does a very nice job of linking all three of these sections together and talking about the importance of using absolute temperature and the relationship of absolute temperature to heat transfer. Okay, so given my recommendation that you go to your textbook, in addition to attending class, paying attention in class, participating in class, asking questions where you need some clarification, I'm going to jump to the bottom line here. And here's the bottom line. For a cycle, for a system operating in a cycle, here's a power cycle, here's a black box. It's got some number of processes. I don't know what they are because it's just a black box, okay? But when all of those processes are fully reversible, that means the cycle is fully reversible. And for no internal or external irreversibility. So everything going on here is reversible. You have to sort of get that in your head. Is this heat transfer from TH into the black box is reversible? The heat transfer from the black box into TL, lower temperature reservoir, reversible. Okay. So get that in your head. Now here is the important conclusion. For cycles that are operating reversibly, and notice how I've drawn in my schematic, I've sort of labeled it reversible to really try to drive this home. The result is that QH divided by QL is exactly equal to TH over TL, as long as you know that TH and TL must have units of absolute temperature. In other words, both both TH and TL have to either be in degrees K or degrees R, degrees Rankine. Okay, so that is an important conclusion. I've stamped it important, but please, and I've double circled it because it is so tempting to write this formula down and say, I've got this formula out of the book. It's really cool. It's really powerful. So I'm going to use it all the time. That's not good. So this formula, this is a fundamental. It's more than a formula. It applies only to reversible systems operating in a cycle, along with the temperatures being an absolute temperature. Very important. So I'm slowing down here a little bit rather than rushing ahead to the next slide. So please kind of try to let this sink in, that this expression, this fundamental, it doesn't apply to everything in the world. Only to systems operating in a cycle, can be a power cycle or refrigeration cycle, either one, okay, but got to be reversible. Okay, so now the question is, what is the best possible thermal efficiency for any system operating in a cycle? And this is going to be a very powerful tool for you. I'm going to move my picture. Okay, here's my schematic. I've labeled my cycle as reversible just to try to drive this home. Okay, I'm going to repeat what we already know. So we should be very familiar with the thermal efficiency, Greek letter eta. Eta thermal is the energy sought over the energy that costs. I can figure it out from there. That's W net over QH. Sought, W net, what it costs us, QH. Got it. Then I'm going to apply the first law to the numerator. QH minus QL is W net. Got it. And then I'm going to write down again from previous slide for reversible cycles, QH over QL equals TH over TL. You can do the algebra now. You can do the algebra on your own. It's done also in the textbook, and get the result. The thermal efficiency, and notice here, I've underlined this, the thermal efficiency for a reversible cycle, so it's not just eta thermal, it's eta thermal reversible is, well, from above, QH minus QL, and that equals TH minus TL over TH. What's the practical conclusion? The practical conclusion here for if you have a reversible cycle operating reversibly, internally and externally, you now have a measure of the maximum possible thermal efficiency for that cycle operating between TH and TL. Your book calls this TC, but you're smart enough to know the relationship. When I use TL, you think TC in your book. Okay, this is a very powerful result relationship. You can count on this being on quizzes and tests that are coming up because it's a powerful tool for practicing engineers as well as student engineers. Okay, a very important practical result. So I'll repeat it again. So for a system operating in a cycle reversibly, everything's reversible, no friction, no unrestrained expansion, no heat transfer across a finite delta T. The maximum possible thermal efficiency based on the second law, is, you can derive, it's TH minus TL over TH. And so this also drives, so you must operate between a hot and a colder temperature. You must do that to be able to operate in a cycle. That's a statement of the second law, okay? You can't transfer all the heat directly into work, okay? And as long as you know what the two temperatures are, there is an upper limit by the second law of the maximum thermal efficiency you can possibly achieve. And so it kind of goes back to my some previous videos where I had the picture of quote unquote anything is possible. This is right in front of your eyes is a demonstration of how not anything is possible, all because of the second law of thermodynamics. Okay, so let's summarize the thermal efficiency and the coefficients of performance all on one page. Let's see if we can do that. So this is a rehash of the previous slide, and I'm going to squeeze all three of our cycles in on one slide. Got to move my picture. Okay, so here's the power cycle. We just covered it. notice here how I've labeled this slide. Thermal efficiency maximum, I've underlined it. Well, here's just this middle stuff applies to any cycle, reversible, irreversible, anything in between. But for a reversible cycle, this over here is true. Very powerful. Next, refrigerator. Refrigeration cycle, energy sought over the energy that costs. Don't need to drag you through the details, do I? We've got QL over quantity QH minus QL. That's true for any cycle. I remember that temperature and heat transfer relationship for a reversible cycle to get the maximum possible, the best coefficient of performance for a refrigerator is TL divided by TH minus TL. Now you've got a number. You've got a maximum possible number. And finally, the heat pump cycle. Okay. Here we go. So for a heat pump cycle, we defined gamma, Greek letter gamma. So the maximum possible coefficient of performance for a heat pump, of course, all this stuff applies to any cycle over here, is going to be TH divided by TH minus TL for a reversible cycle. So now, you know what I'm going to say. I've circled the three performance measures. What do they have in common? You know what they have in common. I don't have to say it again, but I hope you've got that into your head. So that brings us up to a recap of extraordinarily powerful but short video. For reversible cycles only, I've even circled this. QH over QL equals TH over TL. So I know it's tempting. That's the reason I've circled it. The words and the fundamental relationship is it's tempting to use this all the time. You must not do that. You must fully understand what this fundamental relationship applies to. Reminder, temperature units up here must be an absolute temperature, degrees K or degrees R. And what this does, what's the benefit of this? What does it buy us as engineers? It sets the maximum possible performance levels, energy sought over energy that cost, for any system operating in a cycle. And so that's what I've got for you. And that's a very powerful, powerful relationship that enables you to basically calculate one performance measure. And you, as an engineer, you can say, that is the best performance that my proposed system operating a cycle, best performance it can possibly have. I hope that helps, and stay tuned for the next video where we're going to go through some more example problems.